initially neutral metal cans equal an opposite charge.
Get a charged rod.
Negatively charged rod, yeah.
Glue beside one of the cans but not the other.
Okay.
And then split the.
Okay, so the cans are touching in the middle, and what you can do is then just split the two apart. If that's negatively charged, what charge there will be on that can there? Positive, and all the negative will be on that. So charges tend to get attracted to the opposite charges, and the like charge tends to get pushed to the other side. In terms of an electroscope, if I want to charge the electroscope at positive, then I use a negative charged rod. As soon as I bring the negative charged rod close to it, what charge is on the cap of the electroscope? Got positive on the top, and there's negative down below. Okay. As soon as I touch the cap, what happens to the charge from the cap?
Electrons fire through your finger.
Okay. That isolates the base of the. Sorry, that neutralises the charge on the base, and so when I take it away, you're left with the charge from the cap, which is all the positive charge on the cap. So you end up charging an electroscope positive if you're using a negative rod. If you use a positive acetate rod, then you charge the electroscope up negative. Okay, so that's the explanation that you should have. Now moving on to a special case for electric field, where you've got electric field between two plates, which gives you a uniform electric field. So if I had this connected plus or minus to a high voltage supply, because they're two fairly large plates, it's really effectively a large capacitor. The electric field between the two would be joining the two up, and you would end up with what shape of electric field in between two parallel plates like that? Yeah, so we've got straight lines going from one to the other, just crossing that short gap. The bigger the plates are compared to the gap, or the smaller the gap is compared to the plates, the more uniform the electric field is, the straighter lines there are. What you will get, top and bottom, are sort of field lines which run in curves either side, but generally getting quite a uniform electric field. In this case, we've got a much easier relationship between field and potential if we're dealing with a charged plates like that, giving you a uniform field. So I'm just going to run through a derivation that you need to know for how you get the electric field across two charged plates like that, if you know what the potential is. So we'll come back to that in a moment. Two parallel plates. We're assuming that technically the parallel plates are infinite, in that there are no what are called end effects. The end effects are that the field does tend to bulge out a bit. The field will be going in parallel straight lines across here. Which would be the positive, which would be the negative plates? Yeah, so left would be connected to positive, and that would be connected to negative on that side there. So this is, we're assuming that it's a perfect field, that you've got infinitely long plates there. What we're after is, can you get an expression for the electric field in terms of things which can be actually measured for that system there? What you can measure about that is certainly the potential difference between the two sides, because you've got a power supply that you've got at so many 1,000 volts, and you can certainly get the distance between the plates, D. So can we get electric field strength in terms of V and D? To do that, we consider what it would be like if you put a charge across from there to there. Say if there was a charge made that journey, a sort of test charge there, and we just put this small charge here, Q, in the middle there. Make it positive, it makes no difference whether it's positive or negative, but we're just putting plus Q in the middle there. If that charge started on the positive side and made a journey across to the negative side, what would be accelerating the charge from the positive to the negative? Yeah, that voltage difference there. And so what could you work out what the force is on that small charge Q? Yep, Donald? Right, Donald said that would you be using 1 over 4 pi epsilon naught? That equation for electric field strength, or for the electric force, 1 over 4 pi epsilon naught Q over R squared, that's on the basis of spherical symmetry, where it's going out, it's radiating out in all directions from a point charge. Here we've got a special case where it's uniform charge. So we can't use that 1 over 4 pi equation. Trying to get a field. We're talking about the force on there. So what is the force? If we knew what the field was. Say it again. Voltage times the distance. No, that wouldn't give me anything. There is something we can multiply by the distance. Force times the distance will give you the energy, which is used by the charge. So if we can get the work done, force times the distance, that's involving distance, which is what we're after initially. What would which brings me back to what's the force on that charge there? We're trying to find it about the electric field. So what would the force be in terms of that charge Q and the field? Which takes you back to your definition of electric field. What's electric field defined as being? Q. No. No. We're playing alphabet spaghetti at the moment. Think about what is the definition of electric field at a particular point? It's the amount of force per unit charge. It's F divided by Q. So the force on the charge is going to be Tuesday afternoon is never a good afternoon to do this. I knew I was on to a loser. Mrs. Monroe was on. Go on, I want the force on this test charge just being put here in terms of the field and the charge. Thank you. Okay, so we've got F is equal to the force on the charge, multiply the charge by the electric field. So we've got Q times E times the distance there. The force is Q times the field, multiplied by the distance, and that gets you the work done in moving that from there to there. Now, when you do move a charge across a potential difference, what's the equation, another equation for the energy needed to move a charge through a potential difference? QV. So we're going to use work done equals QV. So we've got Q times the potential, V, equals QE times D. And what's the first thing that jumps out? You can cancel the Q. This is why this charge here that we put here is called a test charge, because the charge doesn't really matter, because that charge cancels as soon as we use this equation. So we've got V equals ED, and so electric field strength will be equal to? So electric field is equal to the potential across a uniform field divided by the distance. It's really it's often referred to as a potential gradient, because it's how steeply the potential changes in a particular distance. Bring the distance smaller, what are you going to do to your electric field? You're going to increase it. You're going to make it a much stronger electric field. If you increase the voltage, the potential, you're going to get a much stronger electric field. So that's, again, why it's called a potential gradient. The units are volts and meters. So although the units for electric field strength are normally newtons per coulomb, what would be alternative units for electric field strength? Yeah, so you could have volts per meter as well. So that's one that you not only need to know, but you also need to be able to derive. But the one health warning I've put on is it is only for a uniform electric field. You can't use it in the case of just point charges, as you were doing earlier. Okay, so we'll just put a uniform field only. Okay. So that's one bit that you need there to be able to derive.